From the beginning, I'd like to say it is connected with separately of windows and doors in the trains. It's connected with working of PhD students in Małys in Rabak in Poland. And next, I will say something about materials. It will be aluminium because of life of trains. About experiment and result of discussion, impact strength and breaking core, topographic analysis, and surface analysis, and on the end, conclusions. The paper presented the results of impact bending test, which primarily focused on the surface topography of the resulting fractures. 3 aluminium alloys were used for study. Exactly, aluminium alloy 66 in 2 heats treatment condition, T6 and T64, and aluminium 6063 in T6 treatment condition. These 2 kinds of aluminiums are very often used for production of windows and doors in the trains. In the presentation, the topography and analysis of the fracture surface were also presented. Chemical composition of these 2 aluminiums are put in this table. It's typical aluminiums used in the trains. Mechanical property of this aluminium, it is put in this table. Static strength, it depends of treatment. This is T64. We see that T64, the plastic strength is less than T6. And more, I would like to say, you may see that experiment was made on the stand for impact bending. It was instrument, and it was used in our university. We use 2 kinds of spacemen for bending. It will be here 3 millimeters and 5 millimeters. So the impact is this fix involved on the impact strength. So every time we calculate the experiment of 3 specimens, and here we put a mean value of this strength. So at variant number 1 is fixed samples, variant number 2 is thin samples. So 3 millimeters and 5 millimeters. And on this tape, we put mean value of impact strength and also mean value of breaking wall. So we see, for example, that for aluminium 6063, this C spaceman, the impact strength at breaking wall is less, about 3 times compared to the aluminium 6060. For thin samples, it is similar. You may see also that variant number 2, always impact strength at breaking wall is less compared to thick aluminium. This is very important in the production and in our transport safety on the trains. And here we have the most important photos of samples used in the study. On the left side is variant 1, so it is 3 millimeters. On the and the thick on the right hand. We have in the microscope these photos. And here we may see variant number 1, thick spaceman, that we see that for aluminium 6063, the photos compared to the others. And variant number 2, it's thin spaceman. We also see that aluminium 6063 for photos compared completely other compared to the aluminium 60, it all depends, T6 or T64 treatments. And this is basic, and on the end, we put also other analysis. It was made by Krzysztof Żak. He is not with us, but it is at this analysis results of the surface analysis. This is this surface roughness profiles and surface view for samples from variant 1. It is key. We see how on the length of the tracking during impact bending. And this analysis is for sample Berkeley, and if for variant 2 thin spacements. Also, we put on this diagram. These two figures are very new. And also, we put in one diagram comparison of roughness parameters in relation to the impact strength variant 1 and variant 2. So you see that it depends on the aluminium alloy and also skin or deep specimen. Always I thought that it's mean value, but this mean value is very close to every impact strength. And also, on this figure, it was a comparison of reduced heights of hills and reduced heights of roses, parameter for analysis of impact fracture variants, variant 1 and variant 2. And second comparison is the relationship between steepness and rotation for analysis direction of impact fracture for variant 1 and variant 2 for aluminium. From both this figure, you may see that these parameters depend on aluminium and treatment and things. So analyses are in three directions. And on the end, we put some conclusion based on impact bending test of thin and thick specimen made from two aluminium alloys, 6060 in T6 and T64 condition, and 6063 in T6 condition. The following conclusion can be drawn. At the first, the 6063 aluminium alloy demonstrates 2 to 3 times lower impact faults than the aluminium 6060 aluminium alloy, depending on the space geometry. From the first, it was very easy to find after experiment. For the impact faults of 6060 aluminium alloy, it has been shown that the T64 condition is characterized by greater impact faults than the T6 condition. Also very, very important. The third, microscopic studies of the 6060 aluminium alloy in the T64 condition show a more ductile fracture character compared to the T6 condition. The fourth conclusion is the microscope analysis of the 6063 T6 aluminium alloy, relative numerous voids of various size of the surface, indicating synthetic materials detachment during bending. This resulting surface structure highlights the alloy low energy absorption capacity and tendency toward brittle fracture under impact bending loads. And these two conclusions are very new. It will be necessary more analysis in the future in the paper after the conference, but at the first, you may say that the character of resulting surface is influenced by the space-based size and the initial condition of material. However, when compared the surface roughness parameter in relation to the impact faults, it can be observed that the highest value of roughness and impact faults were obtained for space-based made from the 6060 T6 and the T64 aluminium alloy compared to the space made from the 63 is T6 aluminium alloy, in both cases, reactor of the spaceman size. And the last conclusion, the higher surface roughness parameters were obtained for the larger spacemen compared to the smaller ones. When analyzing the surface in the terms of the relative of the SPT parameters, it reduced per height, and the next parameter reduces very depth. So similarly, this indicates for the surface of the distribution of sharpness relative to the curiosities. So this is all what I would like to say about our presentation.